Welcome to this platform. So in this video, let us have a look at questions from light. Okay, so the first question is this one that we are answering. So figure 7.1 shows a ray of light entering and leaving a glass block. The first question is that name the rays labeled A to D. So we're answering A question. So we are saying A, B, C, D. Now, some of you think A to D is just A and D. D. No. A to D is A, B, whatever is between A to D. Okay, everything between A to D. So the first part here, which is A, is called incident ray. Then for B is called refracted ray. Then for C, it is called emergent ray or diffracted ray. Okay, then D is called refracted, okay, because it's bouncing back, diffracted ray. So these are the answers for the first part. Then on the diagram, indicate I and R for the angle of incidence and refraction. So angle of incidence, we can indicate I there. Then we can also indicate I there, I think. Then we can also indicate R there, also R there. Okay, so that is where you get to indicate. Then question 2, that is C. For a certain piece of glass block, the angle of incidence was found to be 25 and the angle of refraction was 16. Using this information, calculate the refractive index. So you need to know how to calculate the refractive index. So refractive index is just sine I over sine R. And by now you need to know how to state Snell's law. And I'll leave that one up to you. So sine, we are told the angle of incidence. So this I is angle of incidence. So the sine angle of incidence, which is 25, divide sine refraction is given as 16. And now don't act clever here and say sine cancels, then you remain with the 25 divide 16. That is a common mistake some of you might make. So just divide direct on the calculator, punch sine 25, divide sine 34. And you should be able to find 1.53 as that is refractive index. It doesn't have units. Okay. So we've answered that question fully. Let us have a look at this second question. Figure B6.1 below shows a ray of light traveling from water to air. The incident ray makes an angle. So pay attention. The incident ray makes an angle of 65 with a boundary. Most of the light passes through it and passes into air, and it is refracted, making an angle of 56 with a boundary. Now, one thing you should know is the angle of incidence and the angle of refraction. First, you need to know that the angle of incidence is the angle between the ray and, the incident ray and the normal. So where it is striking there, you draw a normal. So a normal is just an imaginary line that is perpendicular to the boundary, or the boundary. Okay, it's just an imaginary line that you imagine is there. So that is the normal that I've drawn. So between the incident ray, which is this one, incident ray is where it is coming from, and the normal, that is the angle of incidence, and not this one. But you need to know that since the normal forms the perpendicular with the boundary, this angle here and also this angle are 90. And that helps you to find the angle of incidence, because in some cases you might be asked that question. So how do you find I here? You're just going to say 90 minus 65 and should be able to find 25 degree. So here it is 25 degree. Okay, then this is moving from water to air. And now you should know what happened when the ray of light is moving from dense medium to less dense medium. Normally it is refracted away from the normal. So normally we can picture this one was supposed to come out in the straight line like that, but it bends away from the normal. And this hole is the angle of refraction. And how do we find this angle of refraction? We are told that this time around, the incident ray and the boundary, this is the boundary, they formed 56, which means there's an angle of 56 here. Now, if that angle is 56, also here it forms a 90 degree. Okay, this forms a 90 degree. So, to find the angle of refraction, you're going to say 90 minus 56 degree. And this is going to give you a 34. So please, you need to pay attention. Don't just go direct and start calculating. In the case they'll find us, we find the question of calculating the refractive index. You cannot use 65 and 56. These are not angles that you are looking for. They form with a boundary. So not one is formed that with a boundary, but between the ray and the normal. Okay. So what is the first question? Complete the ray in figure B 6.1 to show the refracted ray. Label the angle of incidence and refraction. So what I've just done here is just completing the diagram. So I've completed the diagram by indicating how it will come out, and of course indicating the angle of what? The angle of diffraction. But I'm not saying that here you draw these lines that I've drawn that it will come out straight. You just have to know that. So I've completed the diagram. So the first question is answered. Then calculate the refractive index of water. So refractive index is equals to sine I divide sine R. In this case, sine I is 25. So sine 25 is right here. Divide sine, then refraction is 34. Divide 34 degree. Okay, like I've said, you don't cancel out sine, so you just divide. And if you divide sine 25, divide sine 34 is 0.76 as the refractive index. So that is the answer, 0.76. Okay, so for question C, when the angle of incidence is increased, total internal reflection occurs. State one condition necessary for internal total reflection. So one of the conditions is that the ray of light move from dense medium to less dense medium. That is when internal total reflection occurs. And also when the angle of incidence, is greater than the critical angle. Okay, the critical angle is just the angle of incidence at which the angle of refraction is 90 degree. So when it is beyond that, then internal total reflection occurs. And perhaps some of the questions that you might find are, what are the uses of internal total reflection? So it is used in optic fibers, it is used in periscope, it is used in microscope, and quite a number of instruments. So you need to be aware of that part as well. Maybe we might even find that question as we go on questions on light. Then here is the third question that we are answering. That is figure C 2.1, shows a square block of glass KLM with a ray of light incident on KJ. So this is J, please. So KJ. Okay. So this is the KJ. Incident on what? KJ. As you can see from this side. Calculate the angle of refraction. So the angle of refraction, how do you find it? Now look at this. The refractive index of the glass is equals to that one. So now for us to find the angle of refraction, we are going to use the formula for refractive index. Refractive index is equals to sine I over sine R. Okay, to make R the subject is going to be R is equals to sine inverse. Then what are we going to have? Sine inverse. Then we are going to have sine I over refractive index. So that is how the formula is going to be. So now we can replace from here. So we can say sine 60 inside the angle of incidence is that one. Divide the refractive index, which is 1.5, as you can see from the question right here. Then R is equals to sine inverse. So this in the bracket, we divide, then we find the answer, and we are able to find 35.26 degree as the the angle of diffraction. Then calculate the critical angle for the ray of light in this glass block. How do you find the critical angle? So critical angle C is equals to sine inverse, then we have 1 over refractive index. Refractive index, we're still going to use this one. So we're going to have C is equals to sine inverse, then 1 over 1.5. And in this case, if you multiply and find the inverse angle, we are going to find 41.81 degree. So this is the B question, and this is the A question. Then for C, explain why the ray of light cannot emerge from KL, not from here, but instead from L, M. So that is C. So I'll put it, I'll put it right here. Okay, so because the ray of light is refracted toward the normal, and perhaps you might need to know why it is refracted toward the normal and why is it refracted away from the normal if it is moving from dense media to less dense media. So this is just due to change in the speed of light. Okay, then question D, diamond has a refractive index of 2.42. The speed of light in vacuum, that is in air, is 300,000 kilometer per second. Calculate the speed of light in diamond. So how do you calculate the speed of light? So the formula generally you can say speed of light, okay, speed of light, that is in this case you are dealing with diamond, but whichever you are given, that is the formula that you use, equals to speed of light in air divide refractive index. That is the formula that you use. So in this case, speed of light in diamond, we are going to say speed of light in air is this one, 300,000 kilometer per second. Then divide refractive index of diamond is 0.42. I mean 2.42. And if you divide this one, should be able to give you 123,966. I'll put 94 or 9. So units kilometer per second. Okay. Then critical angle for the diamond. So critical angle is equals to sine inverse, then 1 over refractive index. So we have sine inverse 1 over 2.42. And if you find the angle here, you're going to find 24.41 degree as the angle or the critical angle. Then let us have a look at this question. The diagram below shows the appearance of a coin in water when viewed from above. State Snell's law. So this is the question that I've given at some point that you need to state Snell's law. I still maintain you are going to answer it. Then question B, what happened to the ray of light as the surface of water in the diagram above? So the ray of light at the surface is refracted. So the ray of light is refracted. Calculate the refractive index. Now, we are finding a new question here in terms of calculating refractive index. Where we are coming from, we are using angles, but this time around we are going to use refractive index is equals to real depth divide apparent depth. So real depth here is the one that is here, which is the longest one, so 15 centimeter, divide the apparent is 28, 11.28 centimeter. So real depth is just the actual depth, while apparent is unreal depth. Okay, so if you divide these, you should be able to get, what are you able to get after dividing? Should be able to get 1.33. okay, so 1.33 as refractive index. Okay, so let us look at question 7. Figure B7.1 shows an optical pin placed 2 centimeter from the convex. So this is the lens, okay, convex lens, and you know that convex lens, it causes the ray of light to meet. So it is put 2 centimeter. So this is 2 centimeter, the whole of this distance here. The first question is that on the diagram B7.1 above, draw the rays to locate the position of the image. Now, you know the rules how to locate the image of the object. One, you need to know that the line or the ray of light parallel to the principal axis, which is this one, passes through F1. So it is going to pass through this point. So you put it parallel, then of course it passes through that point. Then also the ray of light that passes through the middle part of the optical center, it is not refracted. So one is going to pass there. Then now you join them at the end. Okay, so you join them at the end. They are going to be joined like that. That is where the image is. So like that. So we've completed the what? The ray diagram. This is where the image formed. And you know that the image formed at the back of the object is an real image, uplight, and of course, as you can see, it is magnified. So I've just given you even the characteristics. What is the second question? If the magnification is 3, how far is the image from the object? So magnification, I'll put mg, is equals to 3. Now, how far is it from the object? Okay, how far is the image from the lens? Now, magnification, you can look at the distance moved by the what? The image, divide the distance moved by the what? The object. And in this case, the distance moved by the image, we use v, and the distance moved by the object, we use u. And therefore, magnification, we can say is equals to v over u. We have magnification to be 3. Then the distance from the image, we do not have, but from the object is right here. We've been given that is 2 centimeter. So we put a 2. Okay, so v is equals to 3 multiplied by 2, which is just a 6 centimeter. So that is the distance. Then using the answer in in A above, calculate the focal length. So now, how do you find the focal length? So there are two forms of the formula. So one of them is 1 over f, f being the focal length. Okay, then which is 1 over the distance moved by what? From the optical center to the image, then plus 1 over the distance moved from the optical center to the image. This formula can be easily put in this form: v multiplied by u divide v plus u. And I love using this form because I don't need to reciprocate at the end. So now let us replace, since we have the information, we have this. So we can say f is equals to distance moved by the image is 6. We've calculated it, multiplied by object is 2, then 6 plus 2. We are going to have 12 divide 8. And this gives us what? Should be able to give us 1.5. So that is how we answer this question. Okay. Here is another question that we can answer. So for this one, it is quite more like the questions that we've answered already. So there's nothing much. So let me just read from the statement. Figure B5.1 below shows the ray of light moving from one medium to another. Find the angle of refraction. So angle of refraction is right here, the angle between the ray. This is the refracted ray. So the angle between refracted ray and the normal is what we call angle of refraction. How do we find it? So this is, the whole of this is 90. We have already 65. So you can just say 90 degree minus 65 degree, which gives us what? 25 degree, I guess. So that is the angle of refraction. Calculate the refractive index. So refractive index is equals to sine I divide sine R. So since we've calculated several questions on this one, I'm going to leave it here so you can finish it up. Which of the two medium is denser than the other? Okay, so which one is denser than the other? Now look at this. For you to know which one is denser than the other, you need to know two scenarios. When the ray of light is moving from less dense medium to the denser medium, it is refracted toward the normal. So which means if we were to look at this ray, it was supposed to come out in the straight path there, but it has followed the normal. It has come out and followed the normal. And this is only when the ray of light is moving from less dense medium to the dense medium. And therefore the dense medium is B. But the other way around also, if it is moving from dense medium to less dense medium, instead of coming out in the straight path, it moves away from the normal. Okay, so we can say medium B. Okay, then for this question, figure B6.1 shows the object O placed in front of a thin converging lens or focal length F. Okay, then complete the ray diagram to locate the position of the image formed by converging lens. So we have the object right here, and this is the lens or the converging lens. So what we do? Rule number 1, we draw a line on top that is parallel to the principal axis, and when it hits the ray, it passes through F. So it passes through F. Then the one that passes through the middle, it is not refracted. So the one that passes through the middle is not diffracted. Okay, so just these two, you'd have drawn the ray diagram. But if you want, you can even include the one that passes through F. The one that passes through F, it becomes what? When it hits the ray, it becomes parallel to this. So it becomes like that. So at this point, that is where the image will be formed. Okay, so we've completed the ray diagram. Like I said, even just two are enough. Then state the characteristics of the image formed. So the characteristic of the image formed, look at this. This is at F, this is 2F. So when it is at 2F, also the image is formed at 2F. So one of the characteristics is that the image, the object is the same size as the image. So the object and the image are of the same size. Then what is the other one? The other one, that the image formed is real. So long as it is invented or it's on the other side here, the image is what? The image is real. Then upside down or invented. Okay? Upside down. Okay, or let me just put invented. Okay, then calculate the magnification. So magnification, mg, is equals to, you can use the height of the image divide the height of the object, or you can use the distance moved by the image from the optical center to the distance of an image from the optical center to the distance of an object from the optical center. So which means you can use V over U. So in this case, since they are the same, so I'm just going to have 1 centimeter on top, 1 centimeter down, and magnification therefore is equals to 1. Okay. Then what about this question? The following diagram shows the formation of an image I from the object using the convex lens, not drawn to scale. So this one I've gotten it from multiple choice. I wanted to show you how to find the focal length, but of course the previous we've answered already such a question. What is the focal length? So focal length, I told you the easiest way is V, U divide V plus U. VU is just the same as V times U. Don't get confused here. So now the distance from the center, which is here, to the image is the whole of this one, 23 plus 30, which is 53, multiplied by, then the distance from the here to the image is 45, multiplied by 45, divide 53 plus 45. What is it going to give us? It will give us 23, that is on top, 2385, then divide 98. And this one should be able to give us 24.34. But from the multiple choice, the near answer is 23. So that is how you pick the answers. Okay. Let us have a look at this question. The following diagram shows a dog and a cat standing in front of a plane mirror. Using the diagram, show by construction how the dog sees the cat. So you know that diffraction or a mirror, we are looking at reflection here, the bouncing back of light. So who is seeing who? So how shows how the dog sees the cat. So we are starting from the cat. The rays of light from the cat will go to the mirror. Okay, I've drawn two lines here to the mirror. Then now they will bounce back. Okay, from the mirror will bounce back. Let me just put it like that. Will bounce back and of course enter the eye of the dog. Then now the image will be formed at the back. The image will be formed at the back of the mirror. Okay, something like that. Let me just connect them. So the cat will be seen from here. So this is the cat. So that is how the dog is going to see the cat. So this is refraction. And what you should know is that this distance to the mirror and at the back where the cat is, they should be the same. Okay, so that is how you complete the diagram. Then give two characteristics of the image formed by the plane mirror. What are the characteristics? So characteristics, we can talk of same size as the object. So same size as the object. Then literally invented or invented. Upside down. It is erect. Then we can talk of virtue. It is not real. So quite a number of the characteristics. You can also talk of in terms of distance, as far behind the mirror as the object in front. So they are of same distance. That is at the back and of course in front. So that is how you complete this one. And you might need also to know how to define reflection and of course the uses of reflection. Otherwise we can end here. So please, if you've enjoyed the video, do not forget to subscribe, turn on the notification bell so that you do not miss out our future videos. If you are interested in the online lessons, you can contact the number 0976402563. For GCE, online lessons is 100 kwacha per subject. Science is counted separately, that is physics and the chemistry. Otherwise, see you in the next one.